For decades, the internet has reshaped our world, connecting us in ways we never thought possible. But a new revolution is brewing, one that promises to be even more profound: the quantum internet. This isn't just a faster internet, it's a fundamentally new network. One that could solve problems impossible for today's supercomputers, create unhackable communications, and even redefine time itself. But building it has been one of science's greatest challenges, until now. Quantum Leap, the new network forging the quantum internet. The dream of a quantum internet relies on a simple but incredibly difficult idea: linking individual quantum bits, or qubits, together over long distances. The most promising way to do this is by using particles of light, photons, to carry quantum information between qubits. Think of it like a quantum telephone line. But for years, scientists could only connect a handful of these quantum calls at a time. The systems were fragile, limited, and couldn't scale. Building a large network, the kind needed for a global quantum internet, seemed like a distant dream. Every attempt for larger networks ran into physical limits and diminishing returns. Scale was the bottleneck. How do you link hundreds or thousands of qubits reliably? Until a team in Innsbruck found a new way to think about the problem. Their approach reframed scaling, from isolated links to many qubits speaking at once. Let's see how they did it. A team of researchers at the University of Innsbruck in Austria has just shattered that barrier. They've developed a new method that changes the game entirely. Where previous experiments linked only 2 or 3 ion qubits to photons, this setup is designed for massive scale. Imagine a large ordered array, hundreds of ions held and controlled precisely. Photons stream out from many ions at once, creating a dense, interconnected web of light. This isn't incremental. It's foundational architecture for networked quantum processors. Dr. Ben Lanyon said, "Our method is a huge leap in scalability. This new setup can be extended to much larger registers, potentially containing hundreds of ions and more. Hundreds of qubits, all capable of being networked at once. They are building the quantum equivalent of the first high-capacity internet router, a single architecture that could connect processors across laboratories, cities, or continents. And because the method scales, the path to truly large networks becomes realistic. It is a technical leap and an invitation to build. So what does this mean for our future? This breakthrough paves the way for practical quantum technologies we've only theorized about. First, quantum secure communication, a network protected by the laws of physics. It could make communications fundamentally unhackable. Second, distributed quantum computing, linking many smaller quantum processors into one vast machine. Together they could tackle problems far beyond any single device. Third, quantum sensing, networks of sensors with unprecedented precision. Imagine detecting earthquakes earlier or locating underground resources with unmatched accuracy. As Marco Canteri put it, our method is a step towards building larger and more complex quantum networks. It brings us closer to practical applications like quantum secure communication, distributed quantum computing, and large-scale distributed quantum sensing. Taken together, these capabilities could change science, security, and industry. But the implications go even further than networking. This same technology could revolutionize the way we measure time. The world's most precise timekeepers are optical atomic clocks, so accurate they'd lose less than a second over the age of the universe. By linking these clocks via a quantum network, we could create a worldwide timekeeping system of unmatched accuracy. This wouldn't just tweak GPS, it would enable new tests of fundamental physics and improve deep space navigation. It would create global infrastructure for precision science we can barely imagine today. From better navigation to new physics, the precision unlocked by these links is revolutionary. Time itself becomes a networked resource. The path to a quantum future is being built today, not with cables and wires, but with ions and light. The quantum internet is no longer a question of if, but when.